Cyrus, hi. Hi. Bonjour.
The video now started, so in 12 seconds or something like that, we will be live.
Hi, everyone. Welcome back to track 2 of Azure Community Day, and I'm glad to introduce Marilag Dimatulac, who is not just a solution architect, but also MVP. Hi, Marilag. How long you have MVP status?
Actually, it's just fairly recently. I think it was a year ago. Yeah.
Oh, that's good. That's good. And I expect that everybody want to know secrets, and you tell us about secrets of such powerful database as CosmosDB, right? So floor is yours.
That's right. Cute. Let me just get my presentation here. Hello, everyone. My name is Marilag Dimatulac, and I am a Filipina solutions architect and co-founder of Device. It's a software development company based in Copenhagen in Manila. I am also, like Vladimir has mentioned, an Azure MVP, and I am one of the organizers of Azure User Group Denmark and also Azure User Group Manila. So as you can hear, I'm actually split between two sides of the planet, and sometimes it's challenging but mostly fun. So I'm so happy to be here with you today, sharing the secrets of the Cosmos. And Cosmos DB is really, I would say, one of my favorite Azure services, and it's really close to my heart because in the heart of almost every software that I built over the course of 4 years, Cosmos DB is really like a major player. And it's also very important to me because when I started my own company 4 years ago, we had to build a globally distributed enterprise application that required NoSQL database. And that's how my story with Cosmos DB began. And back then it was just called the document DB. And ever since, I've been following up with all the great uh, product roadmaps and developments over the last years. And I've had some fair share of my challenges also working with Cosmos DB, but so far it has been my de facto persistence layer for all my solutions. And I hope that today I can walk you through some of my own process that I go through whenever I design a new application that would run against Cosmos DB. So for those of you who are still fairly new with Cosmos DB and need a kind of a 1-minute quick tour of what it is about, well, Cosmos DB is the fully managed NoSQL database offering in Azure. And maybe it's much better if I give you a very quick view of how it looks like in the portal. So this is the Cosmos DB interface. And as you can see, you can create a Cosmos DB account. And from here, you can do a bunch of features. So one of the major, most important feature of Cosmos DB is that it's globally distributed. That means if you have a global distributed application, it's so very easy for you to scale your application across all parts of the planet where there's a Azure running in your closest region, right? So, for example, just from the portal, you should be able to set up or replicate your data globally just by clicking some of these cute dots here. And about a couple of like maybe a year and a half ago, it's also now possible to both have multiple write regions, and before it was just multiple read regions. So now it's very easy to set up this global distribution, and you don't have to really worry about everything. And another thing that's really kind of some of the trademark of Cosmos DB is that in a lot of globally distributed databases out there in the market, you would only see normally 2 types of consistencies, but in Cosmos DB you have 5 different consistency. So really based on your requirement. So the most common one is of course a strong consistency, and you would still have the option for eventual consistency or the 3 other ones depending on what your application requires. And Cosmos DB is also a multi-model, multi-API application, meaning that most common NoSQL database would support the document-based database model or data model, and some other products only support graph model. But with Cosmos DB, you have the option to use a document database or graph database or table database or even a column family database, and you can use a lot of different APIs to interact with your database. You can use your SQL API if you're interacting with your document database. You could use a table API. You could even use, for example, other APIs like MongoDB API. If you have a code base that's already working against MongoDB, you can easily port that to Cosmos DB, and you can run it with the same code. And that's also the same with the Cassandra API and the Gremlin API for traversing graphs. So it's really, as you can see, just with that very quick tour, you could already feel that Cosmos DB is such a powerful NoSQL database. And you can learn more about that, of course, obviously, in their amazing documentation. But what I really want to focus on today is how to optimize Cosmos DB. So if you've worked with Cosmos DB before, a lot of people would say that it's quite expensive or it's slow, it's hard to scale, but that's not true. There are many different ways that you can, many different levels that you can optimize your workload on Cosmos DB. So let's say, for example, you're building a new application. Like I said, I want to walk you through my own process when I start building a new application in Cosmos DB. Where do I really start? Where do I begin before I start optimizing? I always try to ask the right questions. What should we really be asking before we go deep into a technical implementation of our persistence layer is that we really have to know what is our app doing. So get to know your app. Where are your users? Where are they in the planet? Maybe your users are just in the same region, or maybe your users are dispersed around the globe. So that would entail different optimization process if your users are spread all over the planet versus just being in the same country. So you also have to understand when is your peak time. Maybe your application is only peaking in the morning, or maybe only in the evening because it's doing some batch processing, or maybe it's peak all the time for 24 hours. I don't know. It's your app. You have to get to know it. But now that you know where your users are and what your peak time is, it's also very important what are the users actually doing at the peak time. So you could see, for example, that you have peak time at around 8 in the morning until 10 o'clock. Okay, that you know, but you also really have to know what is going on between during that peak time. Is there a lot of heavy read of operations, a lot of unpredictable queries, or is there just very consistent write operations where there's some data that's being saved within that time span? Write it down. That is the first thing that you really need to be asking. And once you know that, and it's also very good that in the very beginning to define some of your target. And most of the time, especially as developers, we focus so much on the features. We focus so much on the business process that we need to implement. And that's, of course, very valid. But sometimes we tend to forget to define our target until towards the very end when we have already configured our application, and then only finding out that we are reaching some inconsistencies, or we are reaching some performance issues because we didn't really define our target from the get on. So some of the very basic targets that we really need to define for our system is, first of all, our response time. I mean, really sit down with your architects and think about how fast do you want your system to respond to your user requests? And does it always have to be less than a millisecond every time, or are there operations that can be less than 300, but then some operations more than 300 milliseconds, 500, and maybe even more than a second? Are there some long running processes that would require even a couple of minutes to complete, and that's acceptable? How much do you really know your system? How much response time are you actually committing to your users? That's also very important before you get very technical. And another thing that you need to establish is your availability, and to really understand that there's a difference with the number of nines after your decimal point here for the percentage. So for example, if you're just designing your MVP for your product, do you really have to run your MVP 99.99999% of the time? Or is it expected that you can only target 95%? Remember that every digit in your availability target is translatable to how many hours your system is allowed to be unavailable within an hour, or within a day, or even within a year. So really try to understand, are we okay with having a downtime for 4 hours within a year, and optimize based on that target. And also availability. What is your target RPO? What is your target RTO? And that means how many data loss are you kind of allowed to have before your whole business is disrupted, and how much recovery time do you need if in case your system goes down? So you have to have this put on paper. And then lastly, most important, is that reaching for that response time and reaching for that availability target requires cost. And what is really your budget? You could, if you have unlimited resources, unlimited money, well, call me. No, but what I mean is that you really have to know your budget, because then you have to work within your budget. So there's something has to give. So if you only have a lower budget, and then maybe you could afford being unavailable for a couple of hours, then just reach that. Do not over optimize until you know what your target is. And this is very important when you're designing your database. and designing CosmosDB in particular. And before we get into the other architectural patterns in CosmosDB, I'd like to walk you through into the pricing model, the famous pricing model for CosmosDB. And I think a lot of the cloud services in Azure, for example, have kind of very standard pricing models, but some of them varies in a way. So CosmosDB has also its own pricing model, which is based on actually two things, but I will not elaborate on the first thing, which is storage. You get 10 gigabytes of storage for a certain amount of money, and that's not very expensive, and that's not very complicated because you know how much data you need to store. But what's more important is really understanding the concept of the request unit. So for each operation you do against CosmosDB, each read operation, each write operation that you do against CosmosDB will entail usage of different resources behind the scene: your compute resources, I/O resources, parsing complex query, and all these sorts of things that needs to be taken into consideration. But this is not something that you see, or at least CosmosDB sort of normalized this cost already and then compute the amount of resources that it will take to process your request, and then turn that into, or quantify that into, what you call a request unit. So what happens is, for example, if you need to read 1 kilobyte worth of document, then that is roughly translated into 1 request unit. So if you have a very simple document, 1 KB, then reading that will be 1 RU normally. And then being to write that would require 5 RUs. And then from there, you can then derive based on, again, if you define some of your application targets and application information, like how many users you have and what kind of workload you have, then you should be able to derive, at least in a certain level, how much request units you would need to be able to operate. But there are also other factors that's being considered that affects this pricing. So I already mentioned the size of the document. That means if you have a bit larger document, that would be a little bit more, I wouldn't say expensive. That, of course, obviously that would cost more to read and to write. If you have a little bit more complex query and the way you design your queries, how many joins, levels of joins do you have? How many items or properties are you returning in your select statement? How many number of items do you want to return? So all this also, the complexity of your query can also affect how much request unit you are consuming. And the same with indexing. So CosmosDB has a feature called auto indexing, and that means it indexes all the properties within the document by default. So that means if you have a document, let's say a document that describes a student or records a student information, and that student has maybe 50 different properties, all these 50 different properties will be indexed. And depending on the number of properties that needs to be indexed and their data types, that also affects the request unit for writing and reading this document. So the good thing is, of course, you can tune your indexing later on if you see that, for example, that you are saving a document and you're just querying it based on just a single property and all the time just the same property. So you don't need to index all those 50 properties maybe. So you can tune this and you could potentially lower your request unit. At the same time, with the pricing, you also have to consider your geo distribution. So like I showed you, it's so very easy to replicate your data across the planet. But of course, obviously, you will have to pay for every region, that every read and write region that you add. With the consistency, so if you have geo distribution turned on, you obviously would want to configure your consistency. You can configure this at a using the portal or using code, or you can even configure consistency on every database operation that you are doing. So for example, one specific write operation requires a strong consistency, but not the others. You can configure this also in code. But just so you know that every operation has different request units computation based on the consistency level. So stronger is much more expensive, for example, than eventual. So this is just some of the things that you need to think about when when you're computing your request units. And why is this important? Because in Cosmos DB, you have what you call a reserve throughput. So you actually reserve the amount of request units that you will be allowed per second, or Cosmos DB will serve you per second. So it can range from 400 request units, which is the minimum, which is also for free, up to millions of request units. So it's basically infinitely scalable when it comes to request units. So that's why it's so important for us to understand how that works. And when you provision your database or your containers, you can set this up manually. You can tell Cosmos DB, hey, please reserve 10,000 RUs for me. And that's it. So once you reach 10,000 RU, a bunch of things can happen if you set it to manual. So if you don't do anything about it and all of a sudden you start requesting way too much against Cosmos DB that you are actually exceeding your reserve throughput, you might get throttled. And so, or you will be throttled, and you have to react that. So if you're using the SDK, naturally, this will the SDK will automatically retry until you already the throughput has already gone down, and then it will try to re-execute your operation. So, but the manual mode is best used if you have just a fixed workload in your application. So you actually really know how much data is being written, how much data is being queried, what is the size of your request units, or your how complex is your query, and how often is it happening. So if you have this kind of scenario, then it's and so doing it manually is very much will work for you. And also if you have a much more relaxed service level agreement, so it's okay to be slow at some time, so then maybe manual will also work for you. Then the next method is what we call the auto scale. And this is one of the most requested feature for Cosmos DB, the auto scale. And this has been released just in GA just a couple of months ago. And I'm so happy when they released it, because it has really proven to be very, very helpful when it comes to pricing models, because sometimes it's quite hard to determine your workload. And most of the time in most applications, your workload is unpredictable. So you don't know what kind of queries are happening every second or at any given time. So it's kind of a bit more erratic pattern, the way you users use your application. And if you don't auto scale, like I said, and if you don't manage your reserve throughput or your reserved RU, then you would kind of hit the limit, and then you would be throttled. But with auto scale, so Cosmos DB will automatically scale your throughput up to 10% of the maximum usage. So it will try to intelligently, with its cosmic powers, analyze your operations, and it can see, oh, you're increasing transaction, your queries are getting more complex, there are more users, I can see that you're reaching the maximum that you have set, we will increase it to 10%. And it happens instantaneously. And you can, of course, still set the maximum request unit that you want to auto scale to, because you don't want to just infinitely scale into millions if you don't have budget for that, for example. And so autoscale is really very helpful. But when to use what is something that you have to figure out sometime also yourself after analyzing your workload, because sometimes autoscale is not always the solution, right? So maybe you don't need to autoscale, Or maybe you're auto scaling all the time when you just need to auto scale in a certain period of time where there's peak period. So there are different scenarios. And what I would probably also do is to schedule your scaling, and you can have scheduled manual your manual pricing model. So for example, in one of our application, there's just kind of one operation that requires a lot of resources, and we don't know when that happens. Maybe it happens once a month or twice a month whenever a user triggered that operation. So it will do cross partition scan, it would get a lot of data, it would update a lot of data, but we know which operation it is. We just don't know when the user will trigger it. So what we can do is that whenever that operation is called, we can use the SDK to manually scale our database. And that worked. And after that operation has completed, we can scale it back down and back to the normal pricing method. So that would also work. Or you could also do a scheduled auto scale. So for example, you know that every day at the end of the day, there is like a big bulk operation happening on your database, and then it just happens from the time between 11 in the evening to 1 in the morning, something like that. So you have established that, but you actually still don't know. You cannot still predict how much data will be processed during that time. You just know that it's going to be heavy. So it's still variable. So you cannot define a fixed reserve throughput. You still need to be able to auto scale. So you can also schedule auto scaling when you need to. And based on just some pricing optimization like this, we could see, for example, the 429, we have fixed throttling. So 429, like I have mentioned, is what you get. It's an error that CosmosDB returns if you have reached if you're over your reserve throughput, it will just return 429. And sometimes it's okay because, like I said, it will just recover, it will just retry. And if you don't get 429, that means you're paying way too much because you just always have more throughput than what you're using. So when you see 429, it's all right, as long as it's not, of course, disrupting your application, or not, you cannot reach your SLA because you just keep getting throttled, and then that's not good. But with just a little bit tweaking and understanding and picking the right pricing model would fix this throttling issue. And we've also seen in some of the customers that there's really 40%, around 40% for that particular customer cost reduction just from switching from manual, where they have over reserved their throughput, into converting that into auto scale. So it could be any number of cost reduction. But again, you have to really measure the results and do some POCs, do some load testing, so that you can find out what is the best pricing model for you. You have other options. I have mentioned you could do free tier. You have the concept of reserved capacity, which just means you could actually tell Microsoft that, hey, we actually need this much throughput for the next 3 years. Can we just reserve that? And you will get some cost reduction or some discounts. And if you are still, in your local development, you don't always have to have CosmosDB running in Azure. But of course, now that you have the free tier, then it makes sense, or not that, because before you didn't have the free tier, so it was very expensive to just have your local environment connecting to CosmosDB in Azure. So then they came up with the local emulator, and you could still use this if you want to test the number of throughput, how your application would behave with a certain amount of reserved throughput without having to spin up Azure CosmosDB in Azure and pay for that. So now that we understand the pricing model, it's also important that on the first level, we need to optimize our architecture. So there are three different ways that you can optimize Cosmos DB: optimize your architecture, optimize your data model, and optimize your code. So let's start with optimizing our architecture. In a globally scalable database that has a very low latency SLA, it's important that you partition your data. Otherwise, you cannot scale. If you don't partition your data and you say you have like hundreds of thousands of data stored in your Cosmos DB and you have a lot of transactions, if you don't partition it, that means that Cosmos DB have to carry that entire load in um, in all the regions, and that can be very expensive. So Cosmos DB has found a very, very intelligent way of partitioning your data without you really have to think about it too much, without you having to decide how to shard your data like in other uh, um, NoSQL databases. So this is not something you manage yourself under the hood. But what you do have to think about is which property in your document will be used as a partition key so that Cosmos DB can use that field to group your data into these partitions. So to illustrate, let's say you create a container. Let's say in this case, we have a use case for building a school application. And school application is very centered on student-based operations. So that means I have operations for saving an assignment per student, or saving the student grade, or getting the student's assignment, or displaying a grade for that specific student. So these are just some of the common patterns or read and write patterns for a school system. So naturally, you would think, oh, okay, how do I group my data? So you would have a container. Let's say this is your student container. And from the very beginning, you as an architect have to define which of the properties of the student can I use to group this data logically together. So in this case, let's say you use the student ID. So that means for every student, Cosmos DB would create a logical partition. So all the data about that student, grades, assignments, and some information will go to that logical partition for that student. And then same goes with the other student, right? So, but the logical partition is not your physical partition. So Cosmos DB knows how to intelligently spin up servers or containers under their infrastructure for the actual physical partition where these logical partitions will be stored. And then Cosmos DB intelligently allocates your reserved throughputs across the physical partitions that it spins up. And the physical partitions are being scaled within the region. So it's replicated within your region, and it's also replicated across different regions if you have geo-distribution. And that is how Cosmos DB is able to commit to its low latency SLA. So when you, for example, create an assignment for student one, then Cosmos DB knows how to commit that transaction or execute that transaction in this physical partition. And that's the same if you do it with student two. It will also go to one of the partitions. And for any number of partitions, you can have millions of partitions depending on which partition key you pick. And then Cosmos DB knows where to allocate these logical partitions. You don't have to know that, and you would not know. It's the Cosmos DB's algorithm to know how to group these partitions so that they can be balanced, so that transactions in balance and storage is balanced. And this is very important to know. So we're good with these operations in this partition strategy. But what if now we want to issue queries to get all the students within the same class? And let's say each student has a property called the class ID. So you could easily say or get a query for select all students where C class ID is equals to class 1. That's fine. This will work even if your container is partitioned by student ID. But what will happen then? because you did not tell CosmosDB which partition it should look into, because you only have the class ID, and class IDs exist across all different logical partitions, meaning also across different physical partitions. And then also, because even if this student 1 and student 2 belong to the same class, it doesn't mean that they will be in the same physical partition. They could be distributed across different physical partitions. So that means CosmosDB will scan all these partitions for you, and that can be very expensive. And for very special operations here and there, it's all right. But if this is something that happens all the time, this will easily burden your database. And what if you have to add the class assignment, for example? How if I have to create an assignment for one class, where would I store that in this partition? Because these are partitioned by student ID, so it won't really scale. It won't really make sense. It won't really work like that. So maybe your first thought would be, okay, but then I can just partition by class ID. That means all the students that belong to the same class would be stored in the same logical partition. That would also work, but that could also affect your performance. And then this might also be very imbalanced, because maybe in one class you have just 10 students, in other class you have a lot of activities. So for this operation where you have to get all the students within that class, yeah, maybe it is balanced. But if you go back to the first query, which is to get assignment for that specific student, and then you have partition by class ID, then your operations will be very imbalanced, because like I said, maybe you have more activities or more students or more submission of assignments in one class than the other. So that's also not optimized. So one thing that you could do, and what I would normally do, is to separate my containers into 2 different containers. And now, because CosmosDB for maybe a year or 2 now also supports shared database throughput, which means that your cost could be defined on a database level, and then you could have a lot of different containers under the same database that would share the same throughput reserved for the database. Then you're okay to create containers underneath, because before that you would have to pay for each container. So that's not the case anymore now. You can still do that, but you have other options. So I would try to separate my my container into 2, wherein I have one container that would serve all operations that are very specific to the student, where I can pass a student ID, and then I can partition this container according to students. And then I would have another container that would be best suited to serve the operations that is committed against a class. So maybe I need to, of course, duplicate the data, because in the student container, I still have all the list of students, and then they have a class ID. So technically I can query it by class. But I'm not going to do that. But then I would repeat almost the same data, for example, in the class container, but I would also save the student with a class ID, but I would use the class ID as the partition key. So that way, it's sort of like a materialized view. You have a different snapshot or form or a model of your data in the class container. And there are also a bunch of other things that you can do against the class container, not just to query for students. So maybe a lot of the class-specific operations would go to the class container. And the easy way to maybe duplicate the data or copy the data the way you want it is using the CosmosDB feature called the change feed, where you would listen, or CosmosDB always emits these events whenever a new document is created or updated, and you can use that together with the Azure function, and then you would just run the code and copy this in the other container and set the correct partition key. And if you do this, you could see that your requests are more balanced, the usage of your request units are more balanced, and you would see a lot of performance improvement as well. now that we know about partition key, it's also some of the things that I also think about from the very beginning when I start working with Cosmos DB is how do I structure my resources? And there are different ways. The default way is that you have one maybe database and then a single container. And within that container, you have a lot of different entities or entity types, I would say. And this is sometimes confusing for those of you who have just started with relational database because you would think, oh, okay, so containers are tables, and then in each table I have the same entity. That's not the same in Cosmos DB. So you would have a container, and then you could have multiple entities. For example, in this one, you can have the student grade and the student assignment, which are two different entities stored in the same container as long as they have the same partition strategy. In this case, the student ID as a partition key. And I could also do separate containers like I have maybe previously shown, where I have two containers under the same database. And this will contain students in student-related entities, and this will contain class-related entities. Or I can even do or split my database into two and then have my containers isolated into different databases. And when would I use this? Sometimes you have, if you're building a SaaS application, then sometimes there could be a tenant that has a bit higher resource requirement, and you want to put them in a dedicated database so that you can configure it to just serve that particular customer. And then you would have your smaller customers being routed to another shared database. Or maybe if you are building a microservice-based architecture application, and then you have, let's say, one microservice that is a bit more resource-intensive and has a different requirement for consistency, has a different requirement for geo-distribution, you might want to separate that because you configure these things at the database level. So you have to understand what your application needs. And this is also important because this has some performance implication and cost implication. Like I said, with the pricing, you also can share your throughput on the database level or even in container level. And the next thing that I want to talk about is how to optimize our model. There are different ways or different persistence model that we can use when we are saving our data in Cosmos DB. If you're coming from an RDBMS world, maybe you have seen this type of ER diagram and you're just so used to it. You can make it into your wallpaper if you want to. But we have long since moved away from that kind of modeling and now have accepted that we can actually repeat data. And that denormalization is quite acceptable in the way we also run our applications or workflow in the cloud. So in Cosmos DB, you can have different types of persistence model that I'd like to use. And that's embedded, reference, and separated. This is just my terminologies, but just to illustrate. So one way to model your persistence or store your data is storing all the information about a certain entity in the same document. So that's just embedded. So for example, I'm designing the model for quizzes. And on each quiz, you have like the title of your quiz and description, and you have a set of questions. So all your questions would be in the same document as the quiz document, and then you would just have an array of questions out here. So that's kind of a common structure for document-based NoSQL database structure. But you can easily optimize this, and you can easily have a roadblock if, let's say, your array is unbounded. That means you don't know how many questions there will be. In this case, maybe this is a bad example because you don't know how many questions there will be, but sometimes you don't know how many items there will be in your array. And also sometimes you don't know what is the size of your properties in this document. And if that happens, you cannot control the size of your document. And Cosmos DB has a document size limit. And then also, like we mentioned before in the pricing, the larger the document, the more expensive the call is. So maybe you might want to split that into a different model, which would still yield the same result, but just maybe will use lesser RU or would be faster. For example, one way is to do reference, wherein, let's say, I have the main data about the quiz in one document, and then I would use that ID in the other documents, and I would separate each item in the array into one document each. So I would have question 1 is one document and question 2 is another document. And this kind of referencing is also very useful if you want to get into that specific array item directly by ID. Because in Cosmos DB, if you get an item by ID, and if you're using the SDK and you're using the point read, which uses the read item sync, it's much more efficient to get in, or the request unit is much more efficient if you get into that specific document. So if you want to do that, separate that into 2 different documents. But nothing is stopping you from also just if you have maybe some requirement where you need to page the results of an array, then instead, but you still don't know how many items there is going to be, you can still store them in different documents, but then you can set some sort of a boundary, array boundary for each document. Let's say for one document, I can have max, let's say 3 questions, because I know that the text in question is large and that it can, so that I can prevent my document from getting very big, then I could use this model. And this has a lot of different effect on your cost and your performance when you issue your queries. And there are other ways to optimize. You can optimize your code via the SDK. I have mentioned using the point read, wherein instead of using selects like select asterisk from C, where mentor ID or student ID is equals to ID. So we're so used to issuing SQL statements, but this actually would cost you a little bit more, double, than when you just call or use the SDK's feature called read item async, where you pass the container name and then like the partition key and the ID of that document. So this is much more efficient. This is what will yield 1 RU, and this would yield about 2 RUs. There are other SDK features that you can use whenever you create a Cosmos DB client in your code. Make sure it's singleton. You have to be wary of the location that you're using. Make sure that you're using the closest location to your user. There's a feature for streaming the output from Cosmos DB, serialize and deserialize. If you don't need Cosmos DB to deserialize your document into your objects, just use the stream. And then you have to also look into how to configure your parallelism with max item concurrency. You can also use paging and then configure Cosmos DB to return only a specific number of items. That would also save you a little bit. And look into bulk support if you have to do some bulk operations. Monitor. Cosmos DB has a lot of features for you to be able to analyze your workload. Use them wisely. And in summary, you have to define your target, you have to optimize your architecture, you have to optimize your model, and you have to optimize your code. So that's it for me in Cosmos DB. I heard you learned some of the secrets, and if you want to talk more, just get in touch with me on Twitter. My name is Marilag. Thank you very much.
So it was very good session, by the way, so and good timing. So we still have some discussion in chat happening. So I would like to ask you to answer a few questions if you can. The question was, if somebody has some tables in SQL Server and you need to move them to Azure Cosmos DB, how you can create those tables, because you can't create each table in container, or is there any logic or solution for this?
I wouldn't say there's one formula for just moving SQL-based database into Cosmos DB. First of all, because when you designed your SQL Server-based application, you're really into this RDBMS mindset. And now you're moving into a NoSQL database mindset, and your data would really look very different, and you can design it in a much more efficient way. So that's the first thing that you would really need to think about, instead of just thinking technical and moving tables to containers and how to do that. So you might want to see how you could redesign your models or your database persistence model, or how it's going to look. Of course, there are some tools that you could use to automatically migrate the actual data from SQL into your Cosmos DB containers that you could you could use the SDK also from just migrating, connect to your SQL database and get the data, and then save that accordingly to CosmosDB. But unfortunately, there's no one answer. So start with the modeling and checking out your models, because then from that models, you would know, do I need a container? Do I need 2 containers? Do I need 2 separate databases?
Okay, I see. Thank you. Dimitri, do we have more questions? At least easy questions.
Yes, Yeah, that was a quite extensive answer. Nice. Thank you. Yeah, following the feed, there's no specific questions. There was a discussion on the chat around the question already. Marilag answered, so I'm fine so far. Thank you.
Thank you.
Thank you, Marilag. So that was a great session. Yeah. Now we know all secrets. Thanks for
we
sharing.
don't know all the secrets yet. I would need maybe a whole day to reveal all the secrets. So those are just the basic ones. Yeah, so it does require some creativity.
Yeah.
All right.
Okay. Thank you.
Well, thank you very much, and have a great day ahead. Enjoy the rest of the Virtual Azure Community Day. Bye.
Bye.
For everyone who is upskilling this staycation, we have something very special. The Summer Learner Badger, and you can earn one for joining this event. Scan the QR code, which will appear on your screen, and claim your badger. Azure Heroes is a Microsoft program for recognizing community efforts.